It's a very humble introduction, so it's not going to be very technical and detailed, as you would expect if you're already somebody who has a lot of experience in reverse engineering. It is meant to provide people with a introductory session, like introductory knowledge on how to basically break down applications and tear them down and understand how they work from the inside. And this is really cool because if you are into security, you can really understand what happens under the hood. Now, this is really important for me personally because with the whole trend with ransomware, it becomes really important for all of us security engineers to understand what happens under the hood of each application. You know, that brings a lot of fear to those people out there. So yeah, I think Dr. Mazen already presented, I think he gave a sufficient background about what I do, but just to keep it fast and sufficient, my name is Amin Tajer. You can always contact me at aminatajer.com. I'm also available Twitter and the rest of the platforms. I've got an Instagram at aminatajer.com. So yeah, I've been doing a lot of R&D. I've been doing for most of my career game development, security work, software engineering for the most part. I founded a company and I'm currently the CEO for infiniteware.com. We've been doing this sort of activity and business for almost 10 years. So we have clients that range from Saudi Aramco, and we have STC Bahrain, we've got the Ministry of Interior, a couple more, of course, and we've got banks also. So if you're interested in our in-house applications, in-house AI products, you probably want to go to infiniteware.com and you want to get a tour so you can see what you can get in terms of value for your enterprise. All right, I think that is more than enough about my background in the business. So let's get into it. So the million-dollar question is, what the hell is reverse engineering? And I think a lot of people ask themselves this question, especially if you go online and you go to those technical forums and you're trying to understand what happens, you know, when applications come out. In the world, in the word reverse, and so the phrase reverse engineering is very attached to the whole security space. And so I want to break it down here and give it a bit of thought so we can go forward with the practical aspect. Now, if you really want to take it and you want to summarize the whole thing, reverse engineering is essential just taking things apart and understand how they work from the inside. And so when we apply that to software, it basically means when we have a raw program, when we have an application in its binary format, we want to break it down and understand how it works. Now, if you have ever done any software engineering in the past, if you work as a software developer for a company or so, you'll probably know that the second you compile your application, the second you have that binary format of your source code, it's, for the most part, it's almost I wouldn't say impossible, but it's so difficult to take it. Take it back to its original format, which is a very challenging, honestly, task. If you have something that is worthy of reverse engineering, for example, viruses and malware for the most part. And so, yeah, just to summarize, reverse engineering basically means taking things apart. And in this context, we're talking about software, and we want to understand how they work from the inside. Now, you're probably asking yourself, now, what is really the benefit of doing such a such a tedious activity? What's the point? So I have a couple of points here that I want to share with you guys. The first one is, I myself, I'm somebody who is really fanatic when it comes to understanding what happens under the hood for each thing that I get in my hand. Be it a product, be it a software application, be it even a hardware device, a hardware product in my hand. And so for me, knowing how things work has always been essential to my, to my sense of being. And I think a lot of people share the same sentiment. So if you work with things, you have products in your hand, you always want to know how they work from the inside. And so this is a very cool thing to pick up on. So if you have reverse engineering skills, you'll be able to understand, for the most part, how things work, which is a great advantage when you compare yourself to the other percentile of the people there. The second thing is porting code is important. Now, this is a pretty big deal if you have the, I'll give you an example to understand how this works. Now, imagine if you have an application that works on Linux and you want to bring it to Windows, but you don't have the source code, even though it's very weird to have something on Linux that is not open source. So if you have a product, a software application that lives in an operating system, and that software application is in a closed source format, it becomes very important for all of us to understand how it works so we can port it to other platforms, right? And this is the case with reverse engineering. So for the most part, a lot of products that are out there go under a tremendous amount of reverse engineering, so they can be ported to other systems, to other operating systems, to other frameworks and such. So yeah, this is the second point. And again, reiterating on the subject, stopping malicious code has always been a must. If you work for one of the big companies, let's say Kaspersky, Bitdefender, those security companies, you're definitely going to be looking at people who are so good when it comes to doing reverse engineering. So reverse engineering is integral. It is so essential to the craft of cybersecurity. And the reason is software has always been more of a tangible logic that needs to be opened up so people can understand what happened what happens under the hood. So yeah, there you have it. You've got three things that can get you on your way to understand why reverse engineering is really, really important. Now, a good example is Microsoft Connect. If you've ever been a gamer, you'll know that Microsoft Connect came in back in the day for the Xbox 360. And so the platform, the Connect hardware was basically a proprietary solution that works on Microsoft platforms. It used to work on the Xbox 360, and there was another version that allowed people to use the same device on Microsoft Windows, allow them to do applications on Windows, which was super great, honestly, if you want to do gestural applications. But the problem is, the twist was, if it only works with Microsoft platforms, basically the Xbox 360 and Microsoft Windows, which was a bummer, honestly, because if you have a Linux box, good luck getting the Kinect working on your box, right? So what happened is the open source platform went on a journey, and they wanted to break down the software stack of Microsoft Connect and understand how it works from the inside out. And then they wanted to reproduce the same software machinery in order to have a driver that works, software driver that works on a Linux, basically on Linux platforms, which was a great deal. So they managed to do that, and now even if you have a Connect device, you can also use it on your Linux platform, which is really, really great. So this is a very cool example for reverse engineering that works on porting code, porting products to other platforms. The other example that I want to share with you guys is ransomware. I'm sure that all of you by now, okay, because you're part of this session, and I'm sure you have a lot of interest when it comes to security, you'll probably know that WannaCry is very notorious for being, probably one of the nastiest ransomware applications out there, ransomware malware. So what it does is, if you have no clue what ransomware is, which I really doubt, but nonetheless, WannaCry is a sort of utility that was done by hackers, and it allows the hacker to basically encrypt your hard drive or files depending on the implementation, and then because they're using PKI, which stands for public key infrastructure, a very fancy name for an encryption scheme. What it means is you have a password that is way different than the password that was done for the encryption. So in order to decrypt all of your files, you have to get a hold of that password, the different one from the one that was used for the encryption, which makes it much more difficult for people to decrypt their files. And ransomware does this really, really efficiently and fast. And normally they share their passwords, or let's say the keys in this case, with different servers, and they blackmail people into paying them a ransom so they can decrypt their files for them. And a lot of companies went through this issue. I've personally worked with a lot of clients in Lebanon, big companies that have to do with multimedia and entertainment, and they've been all through the same problem. So if you have a very bad incident with a ransomware, just know that you and among others, face the same issue. But yeah, coming back to the point, knowing how things work allows at least to understand the flaws of such implementation, and it allows us also to create a solution that allows people to fix those issues. All right, now I want to talk first about what it takes for a good reverse engineer, to be able to pick up the craft. The first thing that I really picked up during my career is the idea of software engineering. To be quite honest, reverse engineering is very close to software. You have to understand how software works inside out, how frameworks, how the operating system basically transfers control to the application, how the compilers basically work and translate your application and put it in a acceptable format that allows people to use. And so the idea is, if you want to be in this space, you want to make sure that you have a decent amount of experience when it comes to having a hand in software. So don't think that by the by the mere idea of using Python, for example, and I mean for probably a short time, like 2 days or 3 days, and then you'll be able to be in that space. You have to have a lot of experience with software, and the more you have information about operating systems and frameworks, the better it is for you to to pick it up to pick it up from all angles. All right. So this session is going to be divided into two parts. The first one is going to be a bit of housekeeping. We're going to be talking about the principles that are really important for people to understand what happens under the hood, and a couple of principles about computing and how software works essentially. And then we're going to take it down to actually breaking code and having practical stuff in our hands, which is going to be cool. You can take my word for that. All right. So before we just go in, at any point you have any question, please shoot it here in the comment. I'll be more than happy to help you guys. And again, remember, this session is very casual, so there are no formalities. There's no concept such as stupid questions. So just shoot it out in here, and I'll be more than happy to provide the answer that I know. And then if I don't know anything, I'll probably just say that I know. I don't know. Okay. So chapter 1. Let's talk about a bit of housekeeping. Let's talk about software for a bit. Now, the million-dollar question is, how do computers work, right? And this is really cool because if you look at all the elements that make up, our software stack, you begin to understand how magical the computer industry really is. So it begins with the hardware itself. So you've got CPUs, you've got GPUs, you've got your motherboard and every single thing in here. And the ultimate purpose of the hardware is to just realize whatever that you do in terms of software. So your software basically translates into an intention, into logic, into a software logic, and then that works, that runs on top of the hardware. So we rarely deal with the hardware unless you are a hardware engineer. But for the most part, it's really important, even for veteran engineers, to understand what happens on the hardware. There's a lot of nitty-gritty details, when we talk about CPUs, how they work. You've got different bugs that work on Intel, for example, and other stuff that work on AMD's chips and such. So the more you know about the hardware, the better it is. And yeah, so we've seen a lot of attacks happening lately that target the hardware. So you've got Spectre, and you've got the other one also, Meltdown, that are targeted towards the hardware. So it doesn't really matter if you have an operating system that is well up to date if your hardware is flawed. And this is where getting to know the hardware is a big benefit to understanding how things work. Now, as a application developer, you don't normally work with the hardware itself. It is very difficult to write code that runs on the hardware. You have to pick up probably assembly. You have to understand how to talk to the CPU. The CPU is a very notorious beast that requires a certain protocol in order to talk to, in order to accomplish things. And so it is not really trivial for people to go and do their magic on the hardware directly, unless you're working with an industry like game development, where it is really important to squeeze every cycle out of the CPU. And this is why we have operating systems. So operating systems are basically the glue between your hardware devices and your applications. So think about it as if it was a a contractor of some sort. So your machine is basically your house, and the contractor, in this case the operating system, allows you to get a lease on some of the properties, and it allows you to live in those houses, in these houses. And so you, as an application, in this case a user, don't really have the full access to every single thing. Every time you want to have something, you want to do something important, you have to go through the operating system. The operating system acts like a proxy of some sort. It goes over your request. It validates that it's really reasonable. If you have the authority, if you have the privilege to do all of that, and then it transfers your request with the right protocols and every single thing to the machine and the hardware, and then the hardware just does it. So if you think about it, your hardware strictly talks to the operating system. which is again another authoritative application that takes care of your hardware resources, like your printers, your memory, and every single thing that goes inside your black box there. And then it allows the applications to just submit requests and then get things done. So yeah, this is what happens basically in a nutshell. Now, if you build software, you probably got experience developing for multiple applications. Now, this is really, really cool also if you're a programmer to pick up different languages to understand what happens under the hood for those languages, the pros and cons for each. But if we had to summarize and categorize those languages, we'll probably end up with two categories. You're going to have compiled languages, and you're going to have also interpreted languages. So the compiled word has different characteristics that are really, really different from the interpreted world, and they have pros and cons in each category. So I want to go through them, and I'm going to give you examples for those languages. Now, the compiled world is made of different languages. A good example is the C++ combination, which is very popular if you're doing system design, system programming. Like if we take Linux for the most part, it is actually made of C, which is really weird if you're coming from very, let's say, high-level languages like Python. And you're probably going to see me pick on Python a lot through this section. Well, nothing personal, but it always comes to my mind the idea of Python as the other end of the spectrum. Okay, but yeah, well, nothing personal to my friends there. You've got C and C++ again that make up the most part of those low-level languages. You've got also C# and Java, which are different by a bit. And the reason is C# and Java, even though they get into a compiled format, basically when you use them, you don't just run the program as a script. You have to compile your application into this tangible raw application, no matter what the extension is. So if you're developing for Windows, you're probably going to end up with .exe. But if you're developing for Linux, for example, you're going to end up with .elf. All right? Now, the beautiful thing about this sort of world is that when you compile, you're basically doing a lot of work beforehand. And so it becomes easier when you're on the program because you've already done the translation. And the whole idea behind compilation is that you take your source code written in English-like language, and then you just translate it into a language that your CPU, basically your machine, understands. This is what we call 0-1. The 0-1 language, if you've ever heard about that term before. But basically, you're translating your application and you make it into the native language of the CPU so it can run smoothly, right? So it's faster, it's cool, but it has its own quirks. And one big trouble with that is that you always have to compile when you want to run an application, which is not always convenient if you want to have a sort of flexibility when it comes to running applications on multiple platforms. Now, the other end is the interpreted world, and a lot of languages reside in here. So you got Python again, you got PowerShell, JavaScript, and you have many more also. So the reason we have this sort of interpreted scheme for programming is that you want to have this sort of functionality where you just write an application and you don't need to compile it. You just want to run it on the platform that you're hosting it in, and it becomes easier for you to just do scripts and such, and you don't want to go through the hassle of building things and later on running them. So this is really, really cool as a feature, but the downside, as you probably can guess, is that it is flexible, but it's not really that performant. So it's for the most part, interpreted languages are really, really slow, but they're picking up, honestly. If we had to look at all the advances that are happening in the computer science world and the engineering in general, there's a lot of progress that happens into this space, but for the most part, if you're talking about performance, you're probably going to end up in C, C++, and C# and Java. As I said, they're somehow more of an exceptional case, living in the middle between the compiled world and the interpreted world, sharing some of the characteristics of both worlds. But yeah, if we had to summarize, they've got things that are really, really fast. However, they're difficult to build because you have to have a platform that builds them, and portability is not a great deal. And then you've got the interpreted world where you have different languages that are easy to run, easy to write, but they're not really that performant, even though this sort of taboo is changing as we go. All right. So think enough with the computer science software background. Let us just get into some of the cool stuff in here. Okay, so many of you guys, as probably as I can guess, are .NET developers, right? So .NET is it's pretty much in demand here and behind everywhere else in the corporate world. Because it resembles a very good opportunity for enterprises to have their business logic, their applications in a fast format that runs within Microsoft's ecosystem, be it Active Directory or Microsoft Exchange. So basically, if you work with .NET, there's a huge chance that you're going to be working with Microsoft infrastructure because it's easier for you, and the application will probably integrate really, really well. So .NET is really beautiful because it eases the job for developers. You don't have to write everything from scratch. You've got this sort of, let's say, sugar-coated language that enables you to do really cool applications, be it for the web or for standalone or even mobile these days, without the hassle of writing so much of the low-level code, right? And so a big issue that a lot of people go to when they start with the .NET ecosystem is not understanding the difference between applications that are generated using C++ or C or C Sharp on the other end of the spectrum. Now, the funny thing is, if you develop with C or C++ on a Windows platform, for the sake of example, you'll end up having an executable with the extension of exe that runs on Windows. And if you have a C# application that you also develop using the .NET platform on Windows, you're going to end up also with .exe as an extension for your application. But there's a huge difference between those two files that get generated as you develop applications for this sort of environment. And we're going to go through them. Now, the first thing is, if you're developing with C++, C++ is what we call the unmanaged world. Basically, when you develop with C, C++, your applications translates from that source code format into the language that works on the CPU, on the hardware itself. And so Windows, or in this case, basically Microsoft platforms, from the compiler itself and the linker, every bit of tool that allows you to translate the source code from its textual format to its CPU language sort of thing, goes through a specific structure or a specific scheme that we call portable executable. Again, this is very technical. So if you want to dig in this space, knowing how C++ translates the code into a format that Windows understand, I would really recommend opening in here. I'm going to just go to PE format so you can see my screen, and they're going to find that the PE format is so popular that it has its own page here on Wikipedia, right? So I really advise you to go and read this portion if you want to understand how Microsoft, or in this case Windows, how the compiler takes your source code and put it in a specific structure that is understandable by Microsoft Windows as a Windows executable, okay? So this is the format that gets generated by a C++ program, and then you can execute it on a Windows platform. Now, this exe that gets generated is not going to run when you take it to any other platform. So if I take that exe after I compile it on Windows and I try to be cool and take it to Linux and I just double click on it, good luck. It's not going to work. I mean, you have to have a lot of tools involved, like emulators and such, in order to get this up and running. But natively, it's not going to work out, right? And the reason is because this portable executable format is proprietary to Windows, and it only runs on Windows. And so with .NET, what happens is .NET and Java work with this sort of concept of runtime environment. What we mean by that is that, as you develop your application, you don't translate it to the CPU language directly. So you have a bit of flexibility. You don't put it in a format that is only understandable for the target hardware platform. You build it in a format that is understandable by another kind of application that we call the runtime environment. So if you ever work with Java, you probably know that you have to download what we call the Java runtime environment, the GRE, that really annoying thing that you have to download at the beginning so you can run Java applications, right? Or in the .NET platform, if you maybe remember Windows 7 days, you have to download this .NET framework sort of thing, and then you'll be able to run your .NET applications on the Windows platform. Now, The whole purpose of those set of applications is that they work again exactly. So Nasser is asking here, is it a JVM? Yes, it is a JVM. So it's a not so for Java, it's a Java virtual machine. Uh, but for Microsoft, we call it CLR, or we call it Common Language Runtime. Basically, it's another fancy word for the word virtual machine. So it's a software application that mimics that sort of virtualization between the software code aspect and the target platform. So if I had to summarize it in one word, it's basically just a translator. It's again another translator. So when you have your .NET code and you port it to Linux, even though you have the .exe compiled version, it's not a PE, just like this one. It's not a PE format that runs natively on Windows. It's another format that essentially talks to the virtual machine. Basically, the virtual machine is just a program that reads your code and acts like a virtual machine. So it mimics a hardware device. And then on the runtime itself, on the runtime, it translates that from your virtual machine to that language of your actual CPU. In that case, x86 if you're running on Intel x64, and or x64 if running on a 64-bit platform. So Nasser is asking, is it true for Android and iOS devices? Yeah, that is completely true. And I'm going to get to that in a second. You don't need to worry. Okay, so just the idea is .NET and Java, they take characteristics from both worlds, the interpreted world and the compiled world, and they live in the middle. So they're not completely compiled languages. They get compiled, yes, but in a different language other than the target platform or target CPU. And then this .NET framework or GRE that you download is basically the glue that translates that language in the middle, and then it puts it into that format that the CPU can understand. Okay. Now, this is what we call the bytecode, or basically bytecode. So bytecode is the language that the virtual machines understand. All right. So when you build applications in C# or VB.NET also, or Java, when you compile, you have this bytecode format that is understandable by the virtual machine, and then the virtual machine changes it from bytecode into the target platform. Sorry, to the target platform that your CPU understands, be it an ARM processor or an Intel processor, x86, x64, it doesn't really matter for us as long as the CPU understands it in the very end. Okay, so yeah, and this is beautiful because it allows it again to talk about cross-platform. So a lot of projects that I worked on personally demand that I have an application runs on Linux on Windows, and I also want to do it in a way that I don't want to maintain two source code bases, right? So I want to have one source code base that I build using .NET, for example, and then so just maintain one source code base, and then the other platforms, be it Linux or Windows, they can just run my application given the right virtual machine that I have to download. So Java is a really amazing use case for that. So people who are working with Java know that they can take the executable and run it on Linux or Windows or any platform that supports, Java's bytecode. So Nasser again is asking, Nasser is on fire today. Nasser is asking, is bytecode a series of zeros and ones? Definitely. Yes, exactly. So Hussein is saying, this concept is called platform independence. Yes, it is platform independence at its best. That is completely true. So let's go forward in here. I want to show you examples of both languages. So you got intermediate language, or IL for short, which is the language that C# or VB.NET generate in the end of the day. And you can see on the left side, it might sound or might look like as if it was assembly, but it's not entirely assembly. This is what we call intermediate language, or IL. And the .NET framework understands this language. And I believe this is a standard of some sort. So you can read the standard online also if you want to look how this is really made of of components and such. So Muhammad Al-Naim is asking, is C# a hybrid language, works on Windows and Mac? Initially when it came out, it was only for Windows, to be quite honest, but as the .NET platform is gaining more and more traction, there's a lot of platforms that are now supporting this platform. You've got, for example, .NET Core that runs by default on those platforms. So it works on Mac, Windows, and Linux, which is really, really beautiful. So if you're working on a website, you don't have to worry about running a specific emulation scheme on the target platform or such, because .NET Core by default works on cross-platform, basically cross-platform, right? Coming back to the subject, you've got IL on the left and true assembly on the right. And if you ever work with the x86 architecture, you're gonna definitely pick up on some of the mnemonics here on the right side. And mnemonic is just a fancy word for commands that are written in assembly. So you got push, move, pop, and all these things. These are the commands that the CPU can understand when we were building code that directly talks to the CPU, right? So I just wanted to show the difference in terms of syntax, and probably just to get just a glimpse of what's happening here before we go forward. Okay. All right, let's go with the demo first here. So I've got a set of applications here that I want to show with you guys. There's a very common and popular application that goes by the name of ILSpy. And I had the liberty here to go and try and show you where that lives. So ILSpy, I'm just going to click on that one. ILSpy is basically an application that allows you to look under the hood for any application that you have that is written in .NET, that is compiled in .NET, okay? And this is, again, open source. You've got other alternatives that are based, you've got commercial alternatives and such, but this is a fantastic tool for people who are tinkering with open source products and code, all right? So I've got it downloaded in here. I'm gonna go to my demo files here, apps, and there you've got it. There you have it. You have the ILSpy applications, and I'm just gonna run it, and I'm gonna show you a small demo here. All right, so sorry about that. I have the application here. I'm just gonna start with a fresh vanilla thing in here. Okay, so this application allows me to import a .exe, basically a program from Windows, and examine its underlying code in a way. And we're gonna go through that sentence and really explain it that well. So I've got multiple applications here that I created. A good one is an application that I built using C# here in the .NET platform. Can you guys see the screen? Is it too small? Do you want me to increase it and probably zoom in, or is it good enough? Is it good enough for you guys? Can I get a comment in here? Awesome, awesome. So Anna's saying it's looking good. So yeah, let's go forward. So in this application, which is really straightforward, my application in the main function goes by reading a line from the console, and then I'm putting it as a string, and then I just parse it as a number, and I compare it against 5. If the number that I've put it is 5, I'm gonna print yes, otherwise I'm gonna say no. And just to make sure that I'm not bluffing here, I'm gonna say Control F5. I'm just gonna show here that if I put 7, it is saying no. Awesome. And if I do compile again, I'm sorry, run it again, and I say 5, I get yes. So far so good when it comes to understanding the business logic. However, this application is now when you see it in its compiled format, all right, let me just have more space in here. You're gonna find that in the bin folder, you're gonna find an exe. I'm not sure if you can see this, but it's saying here console app1.exe. This is the deliverable that I get by compiling this application. And this is a good example of, let me just increase the font a bit more for people to understand here. See, based on the request of Muhammad. I think now it's way better. Cool. So if I go to the application again, which is in the .exe format, this exe is built using the .NET framework. And if I take it and I drag and drop it on ILSpy here, voila. If I open it, believe it or not, and this is going to shatter so many dreams for the .NET programmers out there. If I go in here, I can actually see the logic. It's a bit masqueraded, so it's a bit not clear as I wrote it back in here. For example, I've got a variable here that says test, all right? And then here, it got, so I got it as S. So if I have to summarize here, ILSpy is basically a decompiler. It takes your application from its raw format to its original source code format. In this case, with .NET, it's fairly easy because the way .NET is made up, it allows people to take it from its deliverable format from its raw executable format to its original source code format, but with it's a bit of lossy, so it's a bit lossy. This is why the variables, they don't come exactly as we think they're going to come into. For example, instead of test, I had s here as the variable, but nonetheless, the logic, the behavior here is exactly the same. All right, which is really, really beautiful. Now, with ILSpy, it's really awesome that it allows you not only to run an application, but to actually change the behavior. So I'll give you an example. If I go in here, there's a plugin called Reflexel. All right, so Reflexel is this sort of application, sort of plugin that is on top of ILSpy. It allows me to see the IL code of my application. So my main function is fairly easy. You've got simple code in here, and it translates to this source code, to this IL code that runs on the .NET framework. Nadia, just hold your horses for a second. I'm going to get into that. I'm going to show you. So yeah, I honestly have a bit of more experience maybe in the IL code, so I would understand that this line in here is probably going to be translated as that in here in the IL code. So what I'll do right click and edit, and I'm going to change 5 to 6. And what I mean by that is that now I change the logic of my application to compare whatever that comes in through the console against 6, not against 5. It used to be 5, but now I'm going to compare it against 6. And to do it in a fancier format, I'm just going to go to the application here and save as my application, and I'm going to say patched. Okay, so I'm just going to say 3. I've honestly done a bit of rehearsal here just to make sure that I don't get myself embarrassed. So yeah, you've got the executables here, but this is the one that we just generated. I'm just gonna, where is that one? Where's PowerShell? Yes, I'm just gonna run PowerShell in this place, and I'm gonna say console app 3, which is patched. And now if I put 6, I'm gonna get yes. So yeah, I just changed the behavior of the application. Just to show that I'm not bluffing, I'm gonna put the existing 5, and now it's saying no. So what I've done so far is I managed to change the behavior of the application, even though I don't have the source code, which is really, really cool. So a lot of people do that when they want to change behavior, write key generators, or they want to crack applications in a legit way, all right? How can we protect API keys or sensitive information, how it's coded inside them? Yeah, so there are many ways. I'll just continue the presentation because this requires a bit more explanation. I don't want to break the momentum of the presentation, but I'm going to get into that in a second, all right? Going forward, I want to show you something else, all right? So you might think that because you've got ILSpy, you'll be able to put any application in here and just examine the content. And this is not true. You remember when I said that we have 2 exe formats? We've got the PE format by Windows, you know, the native format, and then we have this bytecode IL format that runs on .NET. And the code that I just demonstrated in here is built using .NET. This is why it translates to bytecode, which allows me to go and manipulate the code. But if I go in here and I have another application that I have, MPC, which is media player, forgot the last word in here, but nonetheless, if I put that application, I know it's an exe application, but it was not programmed in C# or VB.NET, I get this message. This file does not contain managed assembly, right? Oh, thanks, Ada. Yes, it's media, media player classic, awesome. So this file does not contain a managed assembly, which translates to this application was never done in C# or VB.NET, so you cannot decompile it. So we don't get that luxury of taking things apart into their original logic, right? And this requires more difficulty, more intensive reverse engineering in order to understand how things work. And I'm going to show that in a second. So for .NET applications that are built on top of the PE format, you require a different set of reverse engineering tools. The one that I have in here, just let me go to this session here. Sorry, I'm going to go to applications. There's a debugger that goes by the name of OllyDebug. So OllyDebug is really, really cool. It allows you to debug EXEs and DLLs also. So this is not a so this is a combination of deassembler and debugger, which are technical terms, but what we basically mean is debugger allows me to go over my application line by line, basically, so I can see and examine the behavior, where the assembler is gonna break down the application in its, you know, assembly format that targets the hardware platform. Let me just run in here. Okay, so I've got a lot of windows, don't mind that. If I try to open an application, I'm gonna choose that media player classic thing. And I choose that, give it a second. It's taking some time, but yeah. All right, awesome. Fantastic. So the application got almost loaded. Awesome, fully loaded. And you can probably see here, it's very small, I know, but the idea is you can see the assembly code that translates, to that application. And it talks directly to my CPU, which is in this case x86, as you probably can get from the commands in here. But the beautiful thing about this is that you can navigate so many things in here. So if you ever worked with assembly, you know that you have the call stack here. Apologies. You have the call stack in here, and then you've got the memory map here also, so you can see what is on inside the memory. And you've got the registers here of the CPU. You've got the stuff that you learned back in your assembly class, EEX, ECX, EDX, every single thing in here. But yeah, generally you have every single thing in here. You can also open the modules. You probably know that when you run an EXE, it doesn't run by itself. It has to load different components. So you've got DLLs working here, and here are some of the examples. So you've got all the debug that is currently running. You've got GDI Plus, which is a module loaded by Windows. So many cool stuff in here. All right, crypto also, RPC, bcrypt. So this application loads a huge amount of libraries in order to make things work. And in this application, I can even change some of the code here if I want to change the behavior. But basically, what I wanted to show is that the ILSpy allows you to do this sort of manipulation, and you can examine the source code, or sorry, the binary in this case, if it's in the .NET platform format, IL, or one of the similarities. So one of the similar platforms. And for the PE format that runs natively on Windows, you've got the other one, which is only debug. Now, this doesn't mean that you only have this working on Windows. You can even have it working on Linux. So Linux doesn't have the PE format. It has it's a different format for Linux. It's called ELF, which again you can also decompile. Not decompile, deassemble. But you're not going to use all debug or ILSpy. You're going to use different set of tools that work on Linux. In this case, we've got what we call IDA. IDA. IDA is a very cool deassembler, and I'm going to share a book later on that takes you through what you can do in order to use that system. So Qusay is asking, what about .NET Reflector? Yes, .NET Reflector is a commercial tool, I believe by Red something, I forgot the name of the company, but they do this in a commercial fashion. But it's basically the same thing. You can open .NET code, you can examine the code and change the content. All right, cool. Is it possible to do reverse engineering to obfuscate Java jar? Yes, definitely, and I'm gonna show you in a bit. All right, let's continue. So I meant to show you ILSpy, Reflexel. I show you some of this. Let me show you some of the obfuscated code. Just talking about what Hussein is asking here. So I've got ILSpy again, and I'm gonna show you one of the application here that are obfuscated. If I open this code here, which is an assembly that I got, you're gonna find a very weird set of characters here lined up, right? So you've got C, P, OK, whatever that means. But when I go inside and I try to see the content, God damn it. So you see this crazy sort of debug message that says error decompiling the code, or even worse, when you find code that does not make sense. So you've got different names, different stuff in here, and so yeah, if you want to go and understand how code works in an obfuscated format, good luck with that. You're gonna have a very rough time. And so if I wanted to just break it down for the people who don't understand what obfuscation is, so a lot of people understood that this is a common issue when building software applications, that people can reverse engineer something for code when it's in the compiled format, and they take it back to its original format. which made it a lot worse for commercial products. And this is why the need of obfuscation came on board. So obfuscation is just taking your code and then going through an engine that somehow makes it random, changes the name of the functions, changes some of the words of the names of the variables, changes a lot of things, and just like a huge, it becomes a huge salad thing. All right, and you won't be able to understand the behavior easily. I mean, technically you can understand it if you put a lot of effort, but it is generally very difficult. And so this is the case with this assembly here. So this application has been through an obfuscation engine. You won't be able to see the content directly. In fact, the compiler I'm using, ISPy, is having a very rough time understanding how this works. But if you run that application, it is going to work. So it's not broken. It is just, it is completely masqueraded into this new format that does not allow hackers to understand what the behavior is. Okay, cool. So we got that out of the way. Let's talk about Android for a second. So you'll probably know from this slide that I have a lot of love for Android. Now, Android is a very cool technical stack. And the way they do this is that they're basing their work in Android on the Linux operating system. I'm not sure if you know this, but believe it or not, Linux is just another flavor of Linux, just to show you that Linux is everywhere, no matter what you do. So this is the simplified Android stack. If I had to summarize it, if I go from up, you've got the application that you write in Kotlin or Java, and then they run on Android frameworks. So you've got call manager, I think, or phone managers for the people who are working with Android. All right, the custom built frameworks by Google, and then you've got Android runtime and native libraries. So if you ever done some work on Android, you know that the Java virtual machine on Android is called Delvik. I'm not sure if they've changed it also, but it's called Delvik as far as I remember. And you've got native libraries that work directly in C or C++. So your code basically benefits from two different worlds. It uses some of the code that was done for Android by Google or any OEM basically in its Delvik format or in its Java format. And then you've got native libraries that are in their C, C++ format that call directly into the hardware. And you have hardware abstraction layer, which is out of the scope, but you've got Linux kernel in the very end. So all of your code talks eventually to the Linux kernel, which is written in C. All right. Now this is cool here because if you think about it, if you do an application, eventually you're using the same Java infrastructure to build code, which allows us also to do a bit of reverse engineering, because remember, Java is very similar to .NET. They're both using the bytecode concept, the platform independence thing that we talked about. And in here, I want to show you how you can do that. So I've got an application here. It's called app-debug.apk, which is the final deliverable that you get when you want to upload your application to Play Store by Google, right? Hey, Yusuf, what's up? Awesome. Good to have you here. So yeah, you've got this APK file. And what happens is, the funny thing, in case you did not know, an APK file is basically just a wrapper. It's just a zip file. So if I had to go and put an extension here that says .zip file, I'm going to be able to see the content of the application. So we're getting closer to seeing the source code, right? So let me just pick up one of those files, the .dex. So .dex is a format which is basically the executable code that runs on the Delvik format for Android. So your Android system basically works with DEX files because it treats them as if they were jar files for Java, right? But if I try to be cool and to jar, sorry about that. If I try to do it .zip here in order to go inside it even more, it's not going to work out. And you know why? Because it's still not in the jar format. DEX is unacceptable so far, right? And so in order to take that from the DEX format into a format that we can tinker with, we have a utility here that goes by the name of DEX to jar, which does exactly that, right? So what I'll do here This is the application. You can also find it on Google if you want to do, a bit of homework. If I try to do and run PowerShell, what I'll do is there's a utility here called D2J underscore. We're looking for just a second. Yeah, D2J dash dex to jar.bat, and as you can probably see it here, right? So what I'll do, I've already placed this before, which is class.x here, the file that contains that we got from the file here. And if I do this, sorry, I forgot to put the name of the file, classes.dex is now, what it's doing here is translating it, it's converting it from dex to jar. And so if we go here, you're gonna find that we have the jar format. You can see the timestamp here, so you see that I'm not lying. So what I'll do now, and again, this is another trivia. If you did not know, a jar file is basically an archive again. So if I do zip here and I put a zip file, voila, now I can see the content. Isn't that great? So yes, if I go inside here, I can see the structure of the application, COM, Android tools, IR, whatever it is. If I go to any application code here, you're gonna find class files, right? So I'll just put the files in here, and I've already done it before, as you probably can see, but I'll put another file just for the sake of example. I'll pick up disable instant run, and I'm gonna have two files that are, ending with the .class extension here. Now .class is no longer a zip file, so you won't be able to do that trick anymore. In order to prove that, if I put .zip here and I run it, and it's not working. So .class is the ultimate executable that runs on your JRE environment, on your Java virtual machine. So for that, we've got another application. And just to summarize before I go and run the application, .class has the assembly code that runs on the Java virtual machine. Sorry, that runs on the Java virtual machine. So it has the same concept as the other one that we've seen, which is the IL code. But it's not IL code. It is code that is specific to the Java infrastructure. And if we go here and we run this application, which stands for Java Decompiler, and I've got the GUI program, but you can also get the console application. You've got Java Decompiler here. And if I open the file here, I'm just going to take this address, not here. Yeah, I'm just going to take this path, put it here. If I go for login.class, give it a moment, and there you go. I basically can now see the source code in its naked format, by Java. So yeah, just answering Nadia, there you have it. You can also decompile jar files, which means to a great extent, you can also reverse engineer the Android applications that you find online, which is, it's very important to understand that this is a responsibility that you have to think about when you do this. Not everyone is exposed to obfuscation, but in case you've done that to a commercial app, make sure you just ping them and you tell them that, hey, maybe you want to explore obfuscation. All right, and you can also see the other source code in here, which is really, really great. We've proven our point. Okay, so going forward, C++ is here to stay. Get used to it. I always tell that to all my friends, especially the people who are really crazy about Python. And here's another trivia. Python actually runs on a C++ backend. So no matter how cool you are in Python, you're always going to use C++ without knowing about it. All right. So yeah, here's C++ here to stay. I want to show you a good example also, which not a lot of people really know about. But if you have a game that was done, being a game developer, I always encounter that. If you have a game that is done using Unity, maybe it's time that you go and explore obfuscation a bit. So this is a game that I have, a demo that I got. I don't remember where, but this is coming back from 2015. When you compile your application, your game in Unity, and you have this executable format, the final version, this assembly, specifically assembly-c#.dll, has the format that we can put in ILSpy, and you can check that out in here. Give it a second. I'm just going to run it here. Cool. I'm just going to delete every single thing so I can have a clean slate. I'm going to do that now. Take it here, and there you have it. How weird is that? So I can see code that was done in Unity, right? So you can see stuff done in the iTween library that I used. I'm not sure if I wrote this code, but nonetheless, you probably can see that every single thing that was done in Unity can be now seen in its naked format. Again, not great for commercial products, but nonetheless, we should spread the word and ask people to go and use obfuscation just to make sure that everything is clean when you have a commercial product, all right? And this works out again because the Unity engine basically compiles its code into an IL code that runs on Mono. So Mono is another flavor, another virtual machine flavor. It doesn't use the .NET CLR or the .NET runtime environment. It uses Mono, which is I believe an open source one, if I'm not mistaken, created by Microsoft in the beginning. So we're kind of saying, what if ProGuard is implemented? Does that create a block to reverse engineering? Yeah, so ProGuard, if I'm not mistaken, is a obfuscation framework, obfuscation utility. It does that before you actually generate your code for production. So you probably want to invest, in then understanding how the tool works, right? Okay, going forward, C++ is here to stay. Again, it's cool if you're using C++, you have more performing code and you don't go over any runtime environment. But the quirk is you always have to compile your code for the target platform, right? So if you have your code and you want to run it on Linux, you have to compile it on Linux to link against the Linux platform, the Linux kernel. But if you want to bring it back to another system, let's think about, like, even if you have another operating system and another CPU that powers that target system, you will probably need to compile again. Because remember, compilation in this sort of world takes it into the language that the CPU understands, not the operating system specifically. It's the CPU that eventually has to run the code. Cool. We've done that. Oh, we've done it already. So we've used Ollie debug to show how you can even, not really decompile, but more of a deassemble exes and see their code in the ex86 format. Okay. You can also do that in DLLs, by the way, not strictly the exes. Now, another form of reverse engineering that I want to share with you guys is the idea of Wireshark. So Muhammad is wondering how much is C++? Very good one. So Bernie Starstop, the creator of C++, is definitely paying me every now and then. So you got me there, Muhammad. Sorry. Okay, so Wireshark and Fiddler are other forms of reverse engineering, but they don't do it basically on the source code base. They just do it, but in a different sort of scheme. So let me show you. So if you are a network engineer, you probably heard about Wireshark, which is a very cool tool that allows you to basically eavesdrop on the networks that you have in here, the interfaces, and allows you to pick up the traffic. So what I'll do here, I'll do for the command line, all right? And I'm gonna do ping google.com for the sake of equal, sorry. I'm gonna put -t so I can have it going here. I'm gonna scan in here, and I'm gonna just wait for a second. Sorry, just gonna do it here on the Ethernet. Give it a second, and there you have it. All right. So the funny thing here, if you actually see the traffic in here, and you can see that this is an ICMP, the ICMP protocol, which translates to this traffic that is going out of my machine to google.com, you can see something you probably did not see before, which is, I've got a string here going from A all the way to, I think, yeah, all the way to here, high at the very end. So when you ping a machine, you're basically just sending text to the other machine and waiting for it to come back to you with a reply. So all of these things are possible because we've got, tools like Wireshark that allows us to go and really eavesdrop on the traffic and see. Now there's another application that I really dig. Okay, so the other application is called Fiddler, and Fiddler is really fantastic because it does exactly the same thing, but however, it doesn't do it on the actual package that we get out of the machine. It only works with HTTP traffic. So if you have an application that uses, let's say, web services or such, you're probably going to be able to do that. So a good example is this application here. And as I run the application, I have Fiddler, because Fiddler itself, the application is asking for information from their website. I managed to go and see their traffic in HTTP. And if I go here and inspect the content, I can see the GET request. I can see the headers that are coming from the response itself. I can see the text view. So these things are really, really great. Beautiful. I mean, if you have stuff that you do, you can always just pick up the traffic and analyze it later on. If if you're interested in seeing how ransomware, for example, transmit their keys or their traffic to their control and command center, basically. As a system as a party would be useful, worth blocking. This is different from the session, but I would say yes. I'll always keep black boxes online. I don't want to give any proof to people that my machine lives on the internet, so I don't want to, expose anything that can get the hacker to probably break into any system. So ICMP, if you don't need it, just remove it and you're good to go. Okay, so this is Fiddler, a very useful tool. And going forward here, obfuscation is basically this idea, just like we've reiterated earlier on, just a couple more lines here. So we have a function written in JavaScript, hello, and it just logs a message to the console. This code with the power of obfuscation can become this, and you can probably tell that this is almost, difficult, not really impossible, but super difficult to break down and take it back to its older format, right? So yeah, complicate your logic whenever possible if you're putting your stuff on the internet for production. My best advice that I can get to you guys, right? I've already shown you obfuscation, and yeah, I just want to close by saying that with great power comes great responsibility. I don't want to sound like a hero coming from the Spider-Man movie, but it's really important to know that with every tool that you learn, with everything that you learn, you can probably, wreak havoc, or you can probably do good things also. So reverse engineering is a very cool tool. It gives you a lot of power to inspect stuff, how they work from the inside, but nonetheless, when you use it in the, in an incorrect context, you can really do a lot of trouble, right? And yeah, basically these are the tools that I wanted to go fast over. I wanted to make sure that I, cover tools and different platforms such as Unity, the engine, and for example, the PE format that we have on Windows and stuff, but that does not mean that this is the end of it. You can also use this on the PlayStation, for example, if you have an executable from the PlayStation, Linux format itself, the ELF, you can use the same tools or similar tools from the same space in order to do that. And before I close the questions and every single thing, I wanted to share that this is one of the best books that I ever read, honestly. This is called the IDA Pro book. And it takes you not only on the tool that I talked about earlier on, which is IDA Pro, it tells you exactly how reverse engineering works, how these tools that I just used, how they're able to accomplish the mundane job of taking a binary 0-1 code that targets the CPU to its textual corresponding code that we see in our Windows system. So this is a great book. Give it a look if you are interested. And yeah, I hope I managed to get you a lot of benefit, guys, today.